Okay, we're back with another way to connect a function, the derivative, and the second derivative. This video talks about how we connect concavity with the first derivative. So this is probably the most difficult of the three to kind of work through. This might be a video you want to take a look at and a second time around as well. Okay, so here we go. We got a function, f, just a polynomial. We can see that the function is concave down to begin with, and then we have ourselves an inflection point, and then the function is concave up afterwards. Okay, classic cubic function. The formula x cubed plus whatever x, that doesn't matter. Okay, all we're interested in is the graph of f right now. Okay, let's talk about the derivative. We know from the song, the derivative is the slope of the tangent to the curve at a point along the way. Hey, yes, exactly. Okay, so let's draw some tangent lines so that we can get into this whole derivative thing, because this is our function, so let's draw some tangent lines. So I'm just going to do this quickly. I've got a tangent line here, another one there, another one there, another one there, another one here, so on and so forth. Sometimes the tangent lines are below the the curve. Sometimes the tangent lines are above the curve. But those are a whole bunch of tangent lines right there. And basically what I've done is I've more or less covered the graph, the black curve, with the green tangent lines. Okay, hopefully that shows up on your screen. Okay, now what's the derivative? Well, the derivative is not the tangent line. The derivative is the slope of the tangent line. So let's make some quick evaluations of these slopes. Okay, so bear with me as far as the exact numbers. I know that they're not going to maybe be entirely what you would agree with, but overall, if we look at these slopes right here, we know that these slopes right here are positive, and that makes sense because our function is increasing. Let's just say that this is a slope of 4 right now. Okay, then this little tangent line right here has a slope of 3. All right, so m is 4, m is 3, and this slope right here will be 2. This slope right there has a rise over run of 1. This slope is 0. That tangent line slope will be -1. This tangent line slope will be -2. That tangent line slope will also be -2. This one will be more like -1. We have another 0 here. And then we have slopes of 1 and 2 and 3 and 4. Okay, so those are the slopes of all the tangent lines that I've just drawn. Okay, I want to take those slopes, and I want to, because right now it may not seem like much because there's a lot going on with the graph, let's just pull the slopes out from the graph. Okay, I'm just going to write them down in order that I just wrote them down, but I'm going to just put them in a sequence here. So if I start with the left side and I look at the slopes, I see I have 4, and then 3, and then 2, and then 1, 0, -1, -2, -2 again. Am I still on the board here? I guess I am. All right, and then -1, 0, and 1, 2, 3, 4. So 1, 2, 3, 4. I'm going to cram them in. Hopefully that 4 is still on the screen. It looks like it is. Okay, so those are all of the slopes that I just pulled off of the graph. Okay, take a look at these numbers in the order that we've put them down. And can you describe this sequence for me? What's going on with the sequence of slopes? All right, we see 4, 3, 2, 1, 0, -1, -2, and then -2, -1, 0, 1, 2, 3, 4. Okay, would you agree that at the beginning, the slopes are decreasing? Yes? 4 down to 3, down to 2, down to 1, all the way until we get to this point right here, -2. Okay, at that spot right around here, all right, now the slopes which were decreasing, okay, now we see -2, -1, 0, 1, 2, 3, 4. All right, that's still on the screen there. So now our slopes start to increase. Okay, and that is not by accident. The curvature that we get in a graph comes off of the idea that the slopes are changing. Remember, the second derivative, which is connected to the curvature from the previous video, the concavity, the second derivative is the rate that the first derivative is changing. Okay, so in other words, the second derivative is the rate that the change is changing. All right, what's the change? Well, the slopes of the tangent lines are the change. We're interested in how those slopes are changing. How are the slopes changing? Well, in this specific example, the slopes are decreasing, and then afterwards, the slopes are increasing. Okay, so if we look at when the slopes were decreasing, they were decreasing from 4 to -2. So here was our 4 and here was our -2. Okay, and if we look at that section of the graph, which goes to right about there, all right, everything prior to that point, well, describe the curvature of that graph. It's concave down, exactly. So a function is concave down when the slopes are decreasing. Now, what are the slopes? The slopes are the first derivative. So a function is concave down when the first derivative is decreasing. Okay? And conversely, we have a concave up function after this point. And what happened? Well, the slopes were increasing. So a function is concave up when f prime is increasing. Okay? Now this is, hopefully this makes sense, but again, this is where things get a little complicated, because remember, we were interested when the function was increasing and decreasing, okay? Not when the function was concave up and concave down, but initially we were interested when the function was increasing. Let's just pick that one instead of increasing and decreasing. The function was increasing when the derivative was positive, okay? So we had to find out when the derivative was positive in order to determine when the function was increasing. Now we're interested when is the function concave up. Well, the function is concave up not when the derivative is positive, but when the derivative was increasing. So it gets kind of weird here. There's a lot of stuff that's going back and forth. Ultimately, though, as an AP Calculus student, you're responsible for memorizing all these connections. And that's what I have on the sheet in the folder for you there. Is that it has all the connections that you're responsible for, but here are two more of them. A function is concave up when f prime is increasing. Function is concave down when f prime is decreasing. Okay. Now let's get to this point. What do we call this point? It's an inflection point, a point of inflection. Okay. What happened at the inflection point? Well, it was right where the slopes changed from being decreasing to increasing. Okay. Let's take these numbers and do one more interpretation of them very quickly, because I know this video is getting long. Okay, these are the values of the slopes at particular points on the x-axis. Let's graph them. So way over here, the slope was 4. So over here, my slope was 4. So I'm going to go over to here, then I'm going to go up 4 units. Okay, and then I go over a little bit, and now my slope was 3. Okay, so I got that, and then my slope was 2, and then it was 1. So I have these points. Okay, then the slope was 0. All right, and then once I got to the y-axis, the slope was -1, so that's down here. And then it dropped to -2, and then it stayed at -2 before it started to increase. So we have this type. If I plot all the points, all the slopes as points on a graph, in other words, if this is the graph of f prime. What I've just done here is I've just done a very basic graph of f prime. Okay, because remember, these are the slopes, and f prime is the slope of the tangent to the curve at a point. So I've just graphed all the slopes that I wrote down here. Now, obviously, there's more of them because I didn't write down all the tangent lines, but there's an infinite number of them, and if we were to connect all of these points, all these coordinates, okay, we would get that curve right there. Well, this, right there, boom. That was the spot where the point of inflection occurred. All right, that was the value of x where it happened. What happened to the graph of the derivative? The graph of the derivative has a relative min. Okay, the graph of the derivative changed from decreasing to increasing. And that's where f has a point of inflection. F has a point of inflection when f prime changes from increasing to decreasing. I'm going to write INC to DEC. Or it could be the reverse of that. If f prime or f prime changes from decreasing to increasing. Okay, so here's more connections. Again, these are a little more difficult. You may want to watch this video a second time. I know I can see it's about 10 minutes long, so but hopefully this makes some sense to you because this is a big part of the AP exam.